Hi and welcome. This time around I'm going to attempt to turn a Morse taper into this piece of cold rolled steel that I've prepared. I have faced it, I have dimensioned it to 1.40 inches, I have pre-center drilled and faced both sides so that the ball bearings have a place to sit to hold the part at an angle when I adjust my tailstock. The largest end of a Morse taper is 1.231, so I left a little extra material to remove when I have this mounted at an angle. So next up, I need to figure out how to set the angle when I adjust my tailstock, off axis here, move my tailstock off axis so that I can turn this taper. At first I thought I would just take my indicator and set a 0, move over a known distance, calculate that height difference, and use trigonometry to figure out what that should be for the appropriate Morse taper angle. Instead, what I thought I'd do was I'm going to create a gauge block that sits on top of this that will fit over this curve exactly. This is 1.402, 1.240 2/10. So I'm going to create a block that will fit on here snugly, and it will be the complement to this angle so that when I take my indicator across here, I should read 0 the entire way. That way it'll be easy to set. So next up, let's make that indicator block. So first up, this is the material I'm going to use in my gauge block. All I'm going to do is make it a fixed diameter that's consistent, but first I need to face the end of this guy because it is way off. Boy, this wasn't the cold rolled section, but it sure doesn't feel like cold rolled. These chips straw colored. The feed rate was actually pretty high. I had the feed rate up at 9 thousandths a revolution. So that last piece of stock I was working on, cold roll. I mean, not cold rolled, even though that's the bin I got it out of in my metal supplier. It was actually stainless steel, and I'm guessing 304 or 18.8. Same thing. And if it was 303, I think it would be easier cutting. That my particular distributor doesn't carry a lot other than those two alloys, so it's probably one or the other, and since it's harder, I'm guessing it's the 304. So I've got a piece of cold rolled I had that fortunately will work, so let's face this guy off and get a move on here. Oh yes, chips look completely different too. And the surface finish is all about crappy cold rolled. Next up is to drill and bore the center out to exactly 1.40 inches so that it matches the bore of the bar that I want it to be the gauge for. Starting with the center drill. carbide tip drill bit. it might actually benefit from a speed up. So let's just try it. Let's jump to 180, see what happens. Maybe nothing good, but it's carbide, so it shouldn't overheat. If it doesn't chatter too much. All right. Next up, boring. Gonna do another 40 thousandths pass. Last pass we had a bit of problems with carbide insert getting chipped and not noticing and screwing up the finish. So, you know, with cold rolled you figure it's screwing, it's gonna suck anyways, but that was particularly bad. So last pass is just 2.5 thousandths. And we sped it up to 680 RPM. All right, so here's the fit, piston fit. Pretty tight in there. Maybe over by a thousandth and a half. So now that I've got this piece, I took my tube mic and I measured both sides on a bunch of points until I found the side where the space between the inside and the outside of this tube were closest to identical. These are within a couple of 10 thousandths. And I used a tube mic. You'll notice it has a curved side on one side and flat on the other. The curved goes on the inside so that the point of it can make contact, and the flat on the outside. So it can be most accurate. I did not buy this because I wouldn't use this often enough to need it, but I got it in a lot of tools I bought, and it turns out to be really useful. And the reason I did this to find the spot that the inside bore and the outside diameter are closest to identical is ultimately when this piece that's going to be cut in half is mounted on the arbor like this. It's pretty tight. I want it, when the pressure's holding it against the arbor, I want the inside surface to make as perfect the contact as I can, because the inside bore is 1 to 2 thousandths oversized, so there is a tiny amount of slop. I want to basically make all that slop on the side that won't be in contact. So now when I get to the vise, I'm going to take 2 V-blocks in the arbor itself, and I'm going to push down and clamp the vise jaws shut here. Then what I'm going to do is I'm going to initially put a flat across here so I have a datum surface. Once I've got that flat, then what I'm going to do is I'm going to take one of the V-blocks, turn on its side, take that flat spot, put it on the bottom, and then put a flat spot on the other side. Now I'll have 2 flat spots, and I can turn this around later when I put the sign bar in there. I'll have a flat surface for this to ride on. So as I was describing before, I took the arbor and put it on some V-blocks and put the gauge block I'm making on the arbor and got this guy as vertical as I could. And then I tapped it down so this guy is tight, so it's pressed hard against the V-blocks by this guy pushing down on it. Now I got to take really light cuts because I'm only catching just the edge of this. So we are going to be taking really light cuts, and we're just going to put a flat on this to give me a datum surface so I can flip it 180 and continue to machine all 4 sides of this with flats. These 2 sides are going to have flats to bear against these jaws when I ultimately put the angle in here. So that's where I'm headed. Okay, so now we won't need the arbor anymore. We're just gonna pop this guy off, flip it over on a flat, mill the other side so I've got a reference flat for that side, and I've got to mark this one uniquely so that I can find it again. So, because this is the side that will ultimately have the angle on it, and so it's important because it's the one that was pushed up flush against the shaft. So my reference side is on the bottom, flat on this parallel, and now I am going to make this guy flat for when I have to put the angle on this guy. So I'm going to make this a wider flat than the other one. We're going to go deeper and go for about 1 inch of width if I can, see how that works out. So maybe I'll take 50 thousandths depth of cut or something like that. We'll play it by ear. Just want to get a good wide flat surface so that when I set up the sign plate in here, I can get this angle right. The reason I chose the direction I'm going in is because the chips are going back that way. Last pass will be 5 thousandths depth of cut, and I think I'll even increase the speed so I can get a better surface finish. 2,000 RPM. Now that we've done this flat and our ultimate angle flat, now we're going to pop this guy in between the parallels, between the jaws this way, and clamp on the 2 flats. Let me just make sure there aren't any chips or anything in here. So the next step is to put an angle on this guy, and it required a little bit of math, unfortunately. So the machinist handbook lists taper per inch for a Morse taper, and note that each Morse taper is a slightly different angle than the others. So I had to actually calculate the angle so that I could use my sign bar. So right here you see that it's 0.05193 inches per inch, which basically means if I go over 10 inches, it's going to go up 0.5193. Just move the decimal place over 1 for 10. I use the tangent, opposite over adjacent, actually the arc tangent, to calculate the angle, which is 2.9727 degrees. Once I had that angle, my sign bar is 5 inches along this side, so sine is equal to opposite over the hypotenuse, which is 5. So 5 times the sine of 2.9727 degrees is 0.2593. And here is my stack of gauge blocks, 0.2593 right here. And here is my 5-inch sign bar. So let me set this up and bring you back. So here's my part at an angle. Here's the sign bar, and here's the stack of gauge blocks down here. And that set my angle at the 2.9727 degrees that I need for Morse taper to make this my gauge. Now you can see why I put the flat on this side and the flats on these opposite 2 sides to have something to grab on. It made it a lot easier than having to try and grab on a circular or a round surface. So we're going to get started cutting soon here. I'd never done this before. I am going to go to the very slowest speed this lathe has to offer, which is 70 RPM, and just see how things move, because again, never done this. It's at a funny angle. So I am going to use a positive rake insert normally for aluminum so that I can minimize the forces on the taper I'm cutting here, because I don't want to push on these balls too hard. So I guess let's just give it a shot here. So at this slow in RPM, I'm not going to be able to move very quickly. I'm at 2.2 thousandths revolution. I might want to speed up that feed rate because we could be here a while. Let's try a couple manual cuts, see how that works. So I made some adjustments. I put my tailstock closer because it was kind of stuck out a lot. I was giving myself a lot of room originally. So we're going to try it again now with the tailstock here so that we can see if the stiffness, because I was getting some weird cutting action going on there because it wasn't stiff enough. I could see the tailstock wiggling, the arm of the tailstock wiggling a little bit, but it was almost all the way out. So let's try it again. So we're cutting the taper, but I'm having a stiffness issue in my setup. I stop the lathe and I yank on the work and it doesn't seem to move at all, but I am getting a little bit of wobble in it. So it's not going to be perfect. I'll keep working on seeing if I can improve it, but the taper is cutting. So I've increased the feed to about 9 thousandths of revolution, up the speed to 300 RPM, and I'm having better results, strangely enough. I tell you, it's not perfect. There is no wiggle at all. I'm taking about 15 thousandths passes right now, trying to take it really easy so as to not side load the ball bearings too much. This is 20 thousandths depth of cut. This is all designed to be a learning experience anyway, so. So here's my observations. One, the positive rate cutter is a good thing. It's helping a lot, but there's still a little bit of wiggling, something wiggling in this setup, and I can't tell what it is because if I grab the work, it is really tight. So I don't know exactly, maybe one of the balls, maybe it's damaged or something. Have to pull that off to find out, you know, like maybe it's broken loose. It doesn't feel like it. There is no slop there, but the other thing I'm noticing is this taper looks way too much. And the only thing I think of is that when they listed the taper per inch, they're talking about on both sides combined, so you need to divide by 2. I would have guessed it would have been taper per inch relative to the center line of the shaft, which would have already divided by 2, but I'm thinking not, because this taper looks way too much. So my gauge and everything else apparently are off. Here, let's take a look with a Morse Taper. So here's a Morse Taper 4. And you can see it's way too much of a taper. So my guess is everything I did was for naught because we ended up with double the taper. So learning experience, I can turn the taper, I can adjust the tailstock correctly. In any case, I'm going to stop right here. It was an interesting experiment, but it appears I have at least double the angle of what is necessary. All right, so the first attempt was a failure. The taper turned out good, but I was off. I was double angle because when this machinist handbook page, when they list taper, they talk about taper per inch. I assumed they were talking relative to the central axis. So I was calculating the angle here. And what they meant was the entire angle divided by 2. So I noticed when I was doing it that the angle seemed kind of steep, and indeed it was double. So Fortunately, I have the other half of this guy, so I can make another angle gauge. First, what I need to do is I need to use this reference surface here, flip it over, just clean up this side so that it is parallel to the other side, and then I need to turn this guy and get it at the appropriate half of the 2.973, which is roughly 1.5 degrees, just under. So we're going to try it again, and this time I have to make a new piece of stock. I've got some stainless, no cold roll. This is 303 stainless. It's more expensive, so I didn't use it to begin with, but it does get a nicer finish, so hopefully that'll be a plus. The next step is to take this guy, which was the cutoff piece of my other gauge block, and I'm going to use this reference flat that I put on there, put it this way, and just run a skim pass across here so that I can make sure that I've got a good reference surface when I do my angle. So we're going to do a skim pass, and we're going to go about 2,000 RPM, and we're going to shoot for about 5 thousandths depth of cut. Just a little tiny cut just to clean this guy up. Alrighty, just got to deburr it. Next up, we'll shoot the angle. So this time around, we got to change our holding scheme a little bit. Still have the gauge block. This is half the height, and had to put the part in another vise, which I'm going to try and clamp into this vise. And since it's hardened material, I'm going to clamp down, rather than clamping on the vise directly, I'm going to put a copper bar in here so that I can really crank on it. There we go. Alrighty. And then we just need to take off a tiny bit of material. And then for my last pass, I'm going to bring it back. I'm going to use a little bit of lube. And we'll do like a 1,000th pass. Alright, so part done. We have our new gauge block at half the angle of the previous one. Just need to deburr it and, we'll be good to go. Pretty decent finish. Minor tooling marks. So here we are, second attempt. I'm using the previous angle block with a magnet to attach to this angle block because the material's stainless steel, so I couldn't have fixed it with a magnet. Anyways, got the new angle, 1-something degrees. It is really persnickety, but there we go. And we're about ready to go, except I set this and didn't put the dog on. So I've got to put the dog on. I'm going to have to reset it, but I'll bring you back when I'm ready. So we're all lined up. We're going to try it again. See if we get it any better this time. Let's go with 4 thousandths of revolution. Everything's solid and tight. I don't know what the little noise is. I had that before and I can't tell what it is because this thing is rock solid. It does not budge. So I don't know. But let's take another pass, see what happens. Let's go with 50 thousandths this time to see how it works. I think I had better luck last time when my feed rate was higher, so I might bump the feed up again. Rather than large depth of cut, large feed, plus the chip breaker works better. Yeah, it's really weird. It wobbles when there's no pressure on it, but while it's cutting, it's fine. So the ball bearings to the workpiece should be static. This is tight. The ball bearings to the workpiece should be static, so I don't know where it would go, because both sides should be static. The only thing I think of is maybe there's flex, because I did bring these to quite a cone, so maybe it flexes, but it seems to work better when I'm turning, so I don't really get it. So here is the MT4 insert that goes instead of the chuck for putting dead centers in for alignment, and here is my taper, and it is freaking tight. It's probably because it's got little high spots on it, but man, it is in there. So it requires a little banging to get out. What I should put is some datum on there and see what kind of contact I'm making. But so there it is. Lesson learned. I made this too weak. The material's not strong enough. I should use something like 4140 and harden it. And then on top of that, I guess I did use something like that, but I guess I made it too narrow, and maybe the braze joint itself is weak, because that was what was wobbling. Because when I finally tracked it down, there was no motion here, no motion there. The ball bearing was wobbling slightly, so that must be it, especially since it's at an angle, so that makes it off-center mass. So after I'm done with this fiasco, I have got to set my taper back to 0 and my tail stock back on the center line. So to do that, I use the adapter that came with the lathe for an MT4. I pop one of my dead centers in one side, and I grab my alignment bar, which is 12 inches long, pull out my indicator, come in. Can be a little tedious, but we'll come down here and we'll set a 0. The beauty is we won't want any difference in this one, so we can set the 0, come down to the other side, which you are probably going to be out of frame for you. I should get down to this side and also find 0. If I find anything, just dial it out directly. Wow, look at that. Boy, the lines on the back of that really are good. Let me just double check that. That's darn near perfect. Yeah, that's actually changing. Look at that. There it is. Dialed in, right on the money. That is perfect. So here are the two arbors, double angle out of cold rolled and the proper angle MT4 out of stainless. And there are some high spots, maybe you can see in the reflection where it's making contact. It's definitely not even over the whole surface. That was probably a given considering the wobble that was there. These guys turned out not to be strong enough, as I mentioned before, and so I need to remake those in a stronger format in the future. I could probably take the angle and make a lot less relief than that and then harden it. Maybe that's the appropriate approach. Anyways, so this project was not a complete failure. I know I can turn a taper, not perfectly, but I could probably turn this now, and with some gentle filing and maybe some sandpaper, I could get this to make much better contact. So anyways, thanks for watching. Hope you found it interesting. Hope to see you next time.